Hello and welcome everyone. I recently came across a TUB describing colorless pip counting, a neat and useful magic trick. So today I will pass the love by explaining the simple math behind the scenes. Simple, but very clever. Let's see it in action first. Here's a position from a game I watched on Heroes. The first step is to go colorblind and pretend all checkers are black. Then, separate the board into quadrants and add 3 times the number of checkers on quadrant 3, your home board, to twice the checkers on quadrant 2 and once the checkers on quadrant 1. Then look at the 4 sub-quadrants, again going backwards from your home board, but this time up and down, and simply add them together. Add twice the first sum to this total, subtract the magical 105, and multiply by 3. The result is a good estimate of the pip count difference, usually correct to within 2 to 3 pips. Now you understand why it's useful. It is undoubtedly the easiest method to obtain an approximate count. And magic, because all steps are baffling, especially the first. How can we all of a sudden ignore which checkers are white and which checkers are black? Let's simplify and examine just 2 checkers. The black checker is at 7, while white is on his 12 point, so black leads by 5 pips. Now switch them. Black is on 13, while white is on his 18, so again, magic. Black leads by 5 pips, a small magic. When we switch, both checkers either gain 6 pips or lose 6 pips, so the difference stays the same. Great. Let's continue working with just 2 checkers. How do we compute the pip count difference without color? We can obviously arbitrarily assign a color to each and do the math, but let me show you a more complicated way. Strange are the way of the magic. We do the total pip count going backwards, here 12 and 18, so a total of 30. Now, to make a full circle, a checker takes 25 pips, so by subtracting 25, we get the pip count of one checker going forward, reversed, here minus 7. So after subtracting 25, we are left with the pip difference. Pause for a second if this is unclear. Finally, for the full board, count pips for all 30 checkers and subtract 15 times 25, 25 for each of the 15 pairs, to get minus 1. This we can call the colorless exact method, and it's too much even for Art Benjamin. Which means we reach the third magical stage, simplification. The crucial step is to lump sub-quadrants together, that is, to move all checkers of the quadrant to the center, as shown on the right. Counting the pip difference after the rearrangement gives 372, 2 away from the correct 374. But look ma, the formula fits on the screen. Alas, it will not fit in the average human brain, so we proceed and move the goalpost 2 spaces to the right. That is, pretend the checkers on the 23 are already in the bare of tray. This helps because 23 becomes 21, 18, and so on, all multiples of 3. And so we can write the exact same formula as 3 times something and the excess, the 2 pips we dropped from each of the 30 checkers. So let's concentrate on the expression inside the parentheses. 7 times the checkers in the first quadrant, 6 times in the second, and so on. Starts to look familiar, anybody? In the first stage of the colorless count, we multiplied the total checkers in the home board by 3 and the one in the outer board by 2. Remember? Then we multiplied the whole lot by 2, giving us factors of 6, 4, and 2. And then we added the 4 quadrants, shown here with a +1 in green. So we basically computed this main expression in 3 easy steps. Now we need to deduct 15 times 25. But we already deducted 60. And at this stage, we do everything in multiples of 3. So we subtract 15 times 25 minus the 60 divided by 3, which is, voila, 105. All magic constants have been revealed. That's almost all, folks. Just a few quick loose ends. First, why does it work so well? The inaccuracy comes from moving checkers to the center. But some movements cancel out. Specifically, moving one checker forwards and one backwards does not change the pip difference. Here, for example, moving 2 checkers from point 1 to point 2 and 2 checkers from 3 to 2 keeps the status quo. Same for the subquadrant next to it. Also note that checkers don't have to be from the same subquadrant. We can continue moving provided 2 checkers can move in opposite directions. So in this position, as you already know, we are left with 2 checkers that can't be moved, resulting in the 2 pip difference. Piles of checkers, especially on the 124 points, can create greater imbalances. But those cases are not typical, and the method is aimed at typical positions. Also, you now realize it will not work if any checkers has been borne off or with checkers on the bar. Although with the bar, there is a relatively easy remedy. You can move it mentally to the 2 or 23rd point and deduct or add 2 pips at the end. It's less intuitive but still manageable. That's all I have to say on this cute method. And if you haven't mastered any other counting method, practice this for 5 minutes and you can save yourself precious seconds when playing live. And remember, practice makes fun. See you later.